Hello students, we are going to try to diagonalize this 2 by 2 matrix. Now, how do I do that? The first thing I need to do is I need to find the eigenvalues and the eigenvectors. And if you remember what the relationship is, we're looking for a v and a lambda so that a acts on v as a constant multiple of v. The lambda is the eigenvalue, v is the eigenvector. So of course, we could rewrite this as av minus lambda v equals 0, but we can't pull out a v because this is a matrix and this is a constant. However, I do know that the identity matrix times any vector is that vector itself. Lambda I v equals 0. So now what I can do is I can rewrite this using the distributive law with matrices. And I get this. Now keep in mind I'm not talking about the specifics of the dimensions. I'm implying that all the dimensions work out. Here, of course, 0 would be the 0 vector with as many entries as v has in it, and we're assuming that a is of the right size as well, that all the sizes fit. But this is what I want. So if I'm going to get this to work, I'm going to need some vector v so that this sends v to 0. Which means that this matrix here has to not be invertible, right? Because if this is invertible, then the solution space to this is just the 0 vector. So I'm not going to get any non-zero vector out of v. So what I want is I want this to not be invertible. Therefore, I want the determinant of this to be equal to 0. So that's the first step. So I want the determinant of a minus lambda I, and I'll write that. This is my A. Now, of course, you wouldn't write this out every step. This is what lambda I looks like, because it's just the identity matrix with lambdas, because each of the entries gets multiplied by lambda. So we want this minus 8 minus lambda minus 5, 10, 7. Minus lambda. And we want that to be 0. So first I'm going to take that. So how do I do that? Well, let's try to multiply this. And of course, we want to be careful whenever we do this because it's always easy to make an arithmetic mistake. I'm going to get minus 5 times 10, which is like plus 5 times 10. So that's plus 50. And here, well, what could I do? Ooh, 7 times 8. Tricky one there. So I'm going to get minus 56. And I'm going to get plus 8 lambda minus 7 lambda. And then I get plus lambda squared. Okay? So, and I have plus 50, of course. We don't want to forget that. So, what do I get? I have lambda squared plus lambda minus 6. And I want this to equal to 0, or to be equal to 0, like I said. So that just means I want to factor this. And since this is a plus lambda, I'm going to get a plus 3 minus 2. That's going to give me a plus lambda there. And I have that. Okay. So what does this tell me? Well, it tells me that lambda must be minus 3 or lambda must be 2. And these are the two values for which I'll be able to find vectors in the null space of this A minus lambda I. So let's try to do that. Let's compute what A minus lambda I is for these two values and find the null space of that matrix. Now, the only way, let's just do it. Let's plug in minus 3 and plug in 2. So this here is my A minus lambda I. So what I want is I want the null space of this. So let's try minus 3 first. We'll call that the first eigenvalue. It doesn't matter which we make the first and which we make the second, as long as we keep in mind which eigenvector goes with which one. So I'll get minus 8 minus minus 3. So that's minus 5. And then I have a minus 5 here, and I have a 10 here, and I have a 7 minus minus 3, which is 10. And that's what happens if we plug in lambda equals minus 3. But remember, I want to find the null space. So what I want to do is I want to solve for this equation right here. Okay? Now, I want to row reduce. Well, I could always make this into 1, 1, 0, and I can subtract, or I can add negative 10 times row 1 to row 2 after that, or add negative 2 times row 1 to row 2 before it. Either way, I get 0, 0, 0. So what is this saying? Think in terms of what this actually means in terms of systems of equations. x1 plus x2 is equal to 0. So if I have the vector x1, x2, I know that x2 is negative x1 from this equation. So that's like having x1 minus x1, or I could just pull out an x1 and get 1 minus 1. And this is the eigenvector for negative 3. This is the entire null space, all multiples of this eigenvector. Yes, I can choose any multiple I want. I'm just going to choose this one. If I wanted to choose, say, minus 1, 1, that would be fine as long as I stuck with it throughout. So then I want to now plug in 2 into here. So here I get minus 8 minus 2. And here I get 10. And now I get 7 minus 2, positive 5. So what can I do? Well, I can add row 1 to row 2. Oh, and I want to find the null space of this, actually. So I add row 1 to row 2. And I just get this minus 10 minus 5. Of course, I could have done this in one step if I wanted to. So this would be like, well, 2, 1, 0, 0, 0, 0. Now keep in mind that this is the x1 column and this is the x2 column. And really what I have is 2x1 plus x2 is equal to 0. Or that x2 is equal to minus 2x1. So any vector satisfying this, we could write it as follows. x2 is minus 2x1. We have an x1 here. I pull out an x1, and I get 1 minus 2. So that is my eigenvector for 2. So to summarize, we have minus 3 with the eigenvector shown here, and we have 2 with the eigenvector shown there. Now, in order to diagonalize, all I do is I take A is equal to E d E inverse. So I'm going to want to take E as my matrix of eigenvalues in order. So E happens to be equal to what? Well, it's 1 minus 1, 1 minus 2. Now, many ways to compute E inverse, but, well, one thing I could do is I could just take the determinant of E, which is going to be minus 2 minus minus 1, which is going to be minus 2 plus 1, or minus 1. And A and D switch places, B and C switch signs. So this becomes minus 1, this becomes 1. These two switch places, and I divide by 1. This is going to give me E inverse. So now all I have to do is I have to write this all out. Now D is just my eigenvalues in order along the diagonal. So I get, for my final answer, A is equal to E d E inverse. And I'm done.